Alrighty, let's talk about the origin of our universe, where we came from. So, we are located in the Milky Way galaxy, and we're about 2/3 of the way out on one of the spiral arms. That's where our solar system is, where the arrow is pointing. And in our Milky Way, we are just one of billions and billions of stars, solar systems, other planets, and this whole Milky Way thing spins around this glowing center. And in the middle of that glowing center is actually a black hole called Sagittarius A star, but it's not one of the super dangerous black holes, so we don't need to worry about getting sucked into it. Things in space are so far apart that we often use light years to describe how far away things are. For example, we are so far away from the sun that it takes light from the sun to reach Earth. It takes about 8 minutes. So that means if the sun were to explode, or right now, we would not know for 8 minutes. That also means that when we are looking at the sun, we are seeing it as it was 8 minutes ago, and you can apply that logic to everything else. If we are looking at an object in space that is 1 light year away, we are seeing that object as it was 1 light year ago. And if you could somehow magically transport to that planet that's 1 light year away and look back at Earth, you would see me teaching this class as I did last year. Same thing applies to 100 light years ago, or 100 light years away, 1,000 light years away. The further away from you are from something, the further back in time you sort of see it. So it's interesting. And right now, light is the fastest thing that we know of. Nothing can travel faster than light. So it's the fastest thing that we've got. All right. So the universe is mostly comprised of galaxies, and galaxies are basically these huge collections of stars. Each one can have billions of stars, billions of planets, billions of solar systems, and they are the main feature of the universe. It's basically how the universe is organized. And we think that there might be as many as 100 billion galaxies right now with what we can see in the sky. And there are 3 different types. You have the elliptical. These are the round ones. They can be sometimes more flat or they can be more spherical. These ones tend to be a little bit older. And then you have these spiral ones. These are the ones with the center with the pretty little arms going around it. Kind of looks like a little spinning top. This would be our galaxy. The Milky Way is a spiral galaxy. And then we have the irregular galaxies. These ones are less common and they don't really have a defined shape. They just kind of look like unorganized blobs. Andromeda would be an example of an elliptical galaxy because you can see it's more round. This is actually the one that's closest to us, and we're actually going to collide with this galaxy in a couple billion years or so. There's another one. This would be another example of a spiral galaxy, another spiral galaxy, and then, like I said earlier, the Milky Way is our galaxy. So whenever you look up in the sky at night, most of the stars you can see with just your plain eye are other stars in our Milky Way galaxy. You need telescopes to see other galaxies and stars from other galaxies. And our galaxy is about 100,000 light years across. So if you wanted to go from one side to the other, you would have to travel at the speed of light for 100,000 years. And then if you wanted to go from top to bottom, it would take you 15,000 light years. All right, so we've talked about where exactly we're located in the universe, so let's talk about where the universe actually comes from. And to talk about that, we need to go back over visible light in the EM spectrum. So when you hold up a prism to a regular white light bulb, the prism splits that white light into all the colors of the rainbow because all the colors mixed together make up white, right? That's how that works. And if you remember, red is the color with the longest wavelength and the lowest frequency. So it doesn't have a very high frequency. It's kind of chill. It's the chillest color of them all. It technically has a long wavelength. Whereas if you compare it to violet, violet has the highest frequency and the smallest wavelength. So it goes from like slow to fast as you go from red to violet. However, keep in mind all these colors are traveling at the same speed. The only difference is that their frequency and their wavelength are different. So theoretically, if I took a piece of violet light and I stretched it out, I made its wavelength longer, I could technically turn it into red light. And vice versa. If I took a piece of red light and I squished it and I made its frequency very small, I could technically turn it into a violet light. All right. So what happens if you hold a prism up to a source of light that is not white? So say, for example, I'm holding up a prism to a yellow light or a green light. Well, green is not made of all the different colors in the rainbow, so if you hold it up to a green light, you would see either green or you would see the colors that make up green. Or if you held it up to violet, like it shows in the picture, it would split the colors of that make up violet into its little thing. So it gives you a rainbow, but not the complete rainbow. And scientists can use this to help us figure out what stars in our galaxy are made out of, and also how far away they are, because stars give off different colors of light depending on what they're made out of and how far away they are. And that is called a spectroscope. A spectroscope is basically a fancy prism. Again, you hold it up to a star's light, and it breaks the colors of light in that star into its own individual rainbow, and you can use that spectrum to figure out what the star is made out of. Now, here's where it gets interesting. So, same concept, but now I want you to think about it with sound waves. So if you've ever stood on the street and an ambulance has passed by you, the sound first starts off with a low pitch, then it gets high as it's really close to you, and then it gets to a low pitch as it drives further away. That concept is called the Doppler effect, and here's how it works. So if say that you are in the ambulance and you're the little machine sending out the sound waves, you're sending out the sound waves at a constant rate, but because you are moving, because the source of the sound is moving, those sound waves are either getting squished together or they're getting stretched apart. So if I'm in an ambulance and I'm driving towards you, I'm sending out sound waves at a constant rate, but because I'm moving towards you, those sound waves are getting squished together, they're getting a higher frequency, which is why you hear a higher frequency. Whereas if I'm the ambulance and I'm driving away from you, again, I'm sending out the same amount of wavelengths per second, but because I'm moving away, those wavelengths are now getting stretched out and you hear a lower pitch. That whole concept is called the Doppler effect. We can stretch and bend waves and make them have a lower or higher frequency. And just like how it happens with sound waves with ambulances, it can also happen with light. I mentioned earlier that if you take a low frequency red wave and you squish it together so it has a higher frequency, it can technically turn into violet or blue. So we call that whole concept with light red shifting and blue shifting. So let's say I'm looking at a star that is mostly giving off like kind of red wavelengths in the spectroscope. If it's giving red, that red light means it is really stretched out, which means that galaxy or that star or that planet or whatever I'm looking at is moving away from me. Whereas if I look at a star and it's giving blue, that squished together light with a high frequency, I know that it is moving towards me. Now, why do I care if stars and planets and galaxies are moving towards or away from me? Well, when we look at the sky, we see that I know the PowerPoint says no galaxies, but it's most galaxies. Most galaxies show a red shift, meaning when we look at those stars or those planets or those galaxies, we see red, which means those things are moving away from us. Their light is being stretched out, they are moving away, they are red shifted. Now there's a handful of things that are blue shifted, which means they're moving towards us. For example, Andromeda Galaxy is blue shifted, meaning it's moving towards us, which is how we know we're going to collide with it eventually. But almost every single object in the sky is red shifted, meaning it is moving away. Now, why is that important? Why do we care about that? Well, we know from common sense that if I throw a ball to the left, we know that it came from the right because it had to come from somewhere. So, if from our point of view, everything is moving away from us, we can assume that all of these objects were once located in the same place, and something had to cause them to move away from everything else, and they're still moving away from everything else. And this is where the Big Bang Theory comes into play. So, because everything is moving away from us, and we can measure how fast they're moving away, we can assume that the universe started all contained together. So like imagine all of the matter, all of the energy in our entire universe concentrated in this tiny, tiny area, and then it explodes. And all of that matter, all of that energy starts to spread out, and as it spreads out, it eventually forms galaxies, planets, comets, asteroids, literally everything that we have in our universe today. And because it exploded with so much energy, that energy has not run out yet, and it is still expanding today, which explains why everything is moving away from us right now. The Big Bang Theory also says that this energy should be evenly distributed. Like if you have all the matter contained together and it explodes, and it kind of explodes evenly, then we should still be able to see that energy today, and we actually can. So, going back to general radiation, whenever something explodes, you would expect to see a lot of energy, a lot of radiation from that explosion. So if our universe technically started with an explosion, we should still be able to see that leftover radiation, right? Well, we can't. Again, when you look at the EM spectrum, the highest frequency part of the spectrum is gamma rays. So we can assume that the universe, in the beginning with the explosion, sent out all of these gamma rays, which are very, very high frequency, very, very high energy. Well, it's been a really long time since the beginning of the universe, and as time has continued, the waves haven't slowed down, but they have stretched out into other parts of the EM spectrum. And scientists predicted that since the beginning of the universe, those gamma rays would have stretched out into the microwave part of the spectrum. Again, microwaves, they're a step up from radio waves, so not quite the lowest frequency, but the second to lowest frequency. So again, gamma rays, high frequency, they would have stretched out into microwaves at this point. So technically, scientists predicted that we should be able to look anywhere in the universe and see evidence of these leftover microwave radiation from the original explosion, and we actually can. It's called cosmic background radiation. And what happened is 30-ish years ago, these guys built this giant antenna to try to help out with Earth communications, but they found that no matter where they pointed their antenna, they were picking up this weird leftover microwave background radiation. And they actually contacted scientists at Princeton who were looking for this exact thing, and they were like, oh my gosh, you found it. So these scientists discovered totally on accident this microwave background radiation that proves the Big Bang Theory actually happened. So those are the two main evidences. We have the whole redshifting thing of the planets moving away from us, and then we have the cosmic background radiation that we see no matter where we look in our universe. Both of those things prove that the universe started, contained in the center, it exploded, and it is still expanding today. And that explains where everything in our universe comes from, all the galaxies, planets, stars, comets, asteroids, literally everything.